Hello, welcome to my video on the Master Theorem. I'm going to give you an example of this and explain what it's for. So let's check it out. So what is the Master Theorem? Well, when we go to analyze the time complexity of an algorithm, we have a problem if it's recursive. If it's recursive, it's not as easy to break down, as I'll show you shortly. We end up with a definition of the time of the algorithm takes that's also recursive. So really the master theorem is a sort of plug and chug method of taking a recursive expression of the time it takes an algorithm to run and solving it to get just a standard big O time complexity. So we're going to do three big steps here. So kind of roughly speaking, three steps. We're going to find something called a recurrence relation for the time, for the algorithm's time. So this is step one. Again, if you're just looking at a regular non-recursive algorithm, this would be the only step. It wouldn't be a recurrence relation. It would just be find the time, then maybe simplify it into big O. First step is to find the recursive statement of time for the algorithm. Then once we've done that, we're going to move to step two, which will mean we'll identify the appropriate case of the master theorem. There's three different cases to it, and it just depends upon a handful of coefficients on which one's larger than the other. Really what that means is depending upon what part of that recurrence relation sort of dominates, as n goes to infinity, it'll sort of converge into one of three different places. So that'll be step two, is to figure out the appropriate case, and then once we've done that, we have the case, and we just kind of simplify and solve it down to regular big O statement. So let's check it out here. I'm going to use binary search as my example. Why? Because it's pretty familiar. It's one of the simpler applications of this. So binary search, we have this algorithm to find whether an array contains a targeted value or not. And this is recursively stated as well. So with the first case on line 3, that means we've run out of array to search in. So this implementation has a high and low index, and it halves the window defined by those two indices each recursive call. So once we get down to the high and low index basically touching each other there at 0, being at the same spot, then we know we haven't found the target we're looking for. The second case on line 5, that means the middle value, what's in the middle of the array, is what we're looking for, and we just return that index. The other two cases are recursive cases, so either if the target's below the current middle, we move to the left, so to speak, so the lower half of the array. Otherwise, the target value is perhaps in the upper half of the array, so we'll move that direction to the right or to the upper half, however you want to think about that. Let's figure out what the recurrence relation is for this. So I went through and sort of marked what all the different the time of each different step in here, each different line of code. So if you remember sort of the rules of analysis from my previous video, we can see that line 2, okay, there's really kind of three things happening there: adding two variables together, dividing by 2, and making an assignment. All those are constant time operations. So for simplicity's sake, that just means all of line 2 is constant time. Again, the comparison on line 3, constant, returning -1 constant, comparing on line 5, a value at a position in an array to a particular value, constant. So all these are constant, constant, constant all the way through. And if you remember, one of the rules I presented last time is if you had an if-else statement, and even if you have if-else, as we have here, we have 4 different cases. The time for that if-else structure, so really lines 3 through 11, is giving the maximum of the different cases involved. So, and notice only one case will run, right? Ever. So the worst case then is, well, line 8. So 8 or 10, there's the same. So what's happening there? So we're gonna, because there's a recursive call to binary search on line 8, we still don't know what the big O of binary search is. I mean, that's what we're trying to figure out. All we can say is it's whatever the time it would take binary search normally, or that T is, T of n is, but it's going to be run on an array of half the size. So that's how I think of it is T of n is how much time does it take to run some algorithm. All we can really say is it's whatever half of it was to run this overall procedure. So basically whatever the array being passed into on line 1 is, whatever that size of that array is, if it's 10 elements down here on line 8, we're calling binary search on 5 elements. So there's just a reduction by half. So that's all we really know is, well, whatever the overall time is for binary search, this is half of that. So down there, as I've written down at the bottom of the image, down by line 11-ish, we get the recurrence relation for binary search to be T of n equals T of n over 2 plus order 1. And why is it plus order 1? Because every other operation in this function, ignoring the recursive part, so if you just forget line 8 and 10 even exist, if those lines don't even exist, everything else is just constant, so we just throw that on the end. Now I'm going to throw, technically you should, if you want to be pedantic, it should be, so big O, I haven't really talked about this, but theta O, that's a tighter bound than big O, which is worst case upper bound. Theta is basically rough equivalency up to a constant. That's sort of a tangent. I don't know if that distinction in practice, basically only people who are really in the theory of CS care about this. In practice, everyone talks about just big O, so I'm just going to do that. Technically, just know that there's a caveat there. I should probably say theta O. Theta 1. So, just don't scream at me in the comments, I guess. But anyway, so I'm saying that recurrence relation for the time for binary search is what's stated down there. T of n equals T of n over 2 plus big O 1. Okay, so and this is the problem, right? That we have the time is something recursive. We can't sort of simplify this down with the previously mentioned rules, because we have, the T of n is defined in terms of itself, okay, i.e. it's recursive. So we don't know what to do yet. Okay, so let's move on to, well, what is the definition of the Master Theorem? So I got this out of the textbook I used to use, Data Structures Algorithm Analysis by Weiss. So this, if you're comfortable with math, this looks fine. If you're not, this looks scary. But what is this saying? We have this on that first line. It says the solution to the equation T of n equals A times T of n over B plus theta. There's that theta that I mentioned before. You can just think of it as big O. It's fine. Big O of n to the k log p n. So what does this mean? So that is just what I read right there, that A times T, etc., recurrence equation there is really our template. And what the master theorem does is I promise to sort of plug and chug. That's really the template we're gonna, maybe you can already see the parallel between what I just discovered with binary searches recurrence relation to this, but we're gonna basically take binary searches recurrence relation, adjust it slightly with some algebra, and get it into this form. And then once we have it in this form, there's just a few sort of constants or coefficients here. A, B, K, and P. So what's the deal with these? Well, we're going to compare, and I'll break this down in more detail in subsequent slides, but we're going to compare the quantity A, whatever it is, in the case of binary search is just 1, versus B raised to the power K. And those quantities, we only have 3 choices for them. Either A is larger than whatever B to the K is, A is equal to it, or A is less than it. And as I was mentioning before, which one of these terms is bigger, or if they're equivalent, it determines how the math works, and how it really ends up being this series, what it sums to, so what it kind of converges to. So the ratio of, or let's say, you could say the ratio, but really comparing these two different quantities gives you one of these 3 cases. So if A is larger than B to the K, so let's say A, for the sake of argument, for getting binary search even, was just 2, and B was 2 to the 0, then you would end up with 2 is greater than 1, so that would be the top case. And we'd use that big O there. Versus if it works out that, A is 2 and you have B raised to the power 1, you have 2 equals 2, then you're in the middle case, etc. So just depending upon which, so just depending on the algorithm you're analyzing, you're going to end up with a different recurrence equation. You're going to get different values for A, B, K, and P. And then you just compare them and you pick out the right case. So anyway, so let's continue on with the binary search example. As I said, the master theorem has this template line here. I'm calling this sort of a template recurrence equation with A, B, K, and P in it, right? So it's stated there at the top. Down below, we have what I previously discovered with binary search. So for binary search, we have T of n equals T of n over, or T n over 2 plus, I change it in this one, the theta 1. Don't freak out, you can just think of it as big O. Alright. So let's make the binary search recurrence relation basically fit the form of the master theorem one, and that's all I've done here. So down below you can see I have T of n, what I have equals T of n over 2 plus theta 1. Then I was, just remembering a little bit of sort of, I don't know, algebra, pre-algebra, something like this. We have that equal to T of n over 2 plus theta. And now look up in the master theorem template, we have that n to the k log to the p n. Well, that didn't exist. We just had theta 1. It's just constant theta, right? So we do that trick of taking a quantity, raising it to the 0th power. That means that's just going to be 1, right? So you can take any number. 100 raised to the 0 is just 1, right? So the fact that I had previously theta 1, meaning just some constant value, okay, I can just rewrite that as theta n to the 0 log to the 0 p. And that just means there's this nice alignment here between the Master Theorem sort of template, as I'm calling it, and the binary search recurrence relation. So if we look at in the Master Theorem template, we have A times T of n over B, so that A is the coefficient out in front of T, right? So they'll make that align with binary search. What do we have for binary search? We just have T of n over 2. That means it's implied there's a 1 there, right? So A equals 1. Another way to think about this is like, what values do I have to plug in for A, B, K, and P to make it match exactly what I have for binary search? So we use a 1 for A, okay, and that aligns the two. Now we have n over B. In the binary search recurrence relation, we have n over 2, so that means B equals 2. And because of my sort of algebra, pre-algebra tricks, I, by rewriting 1 as n to the 0 and log to the 0 n, by rewriting 1 as that, I can see that to make these two recurrence relations align, I set k equal to 0 and p equal to 0. And that's what we're really trying to sort of get out of this, is the values for these coefficients that align the Master Theorem sort of template recurrence relation with the particular one for the algorithm we're trying to analyze. So now I've done that. Now I have A equals 1, B equals 2, K equals 0, and then P equals 0. Fantastic. Now, let me move on to, well, what do we do with it now? As I mentioned before, we just have to compare these quantities. So remember, I have this alignment here. Now we just need to compare A versus the quantity A versus the quantity B to the K. And just logically, it can either be A is less than B to the K, A is greater than B to the K, or it's equal. There's not really any other option. So now we have the particular values from the alignment with A equals 1. B to the K, we end up with it's 2 to the 0, which is 1. Thus, we're in the middle, that middle case, A equals B to the K, right? Because A is 1 and B to the K is also 1. So that means we're in this A equals, we're in the middle case here, where A equals B to the K. So we're going to just pick out that big O of n to the K log P plus 1 n. So that's what applies to binary search. If you do a different, run this analysis on a different algorithm, you have different values for A, B, K, and P, you may end up in a different case. For binary search, we end up in the middle case because, again, the quantity A is equal to the quantity B to the K in this case. So what does this mean? We just need to do a little bit of simplification. So I pull out that big O complexity. So now we have T of n is really O of n to the K log P plus 1 n. Now we just, again, plug in the values A, B, K, and P, and we see that down below I have big O of n to the 0 log 0 plus 1 n. Simplifying that, we just end up with O of log n, which is great because that sort of matches at least our sort of intuition or maybe prior knowledge of what we expect the answer to be, that binary search, we have an array, each step we cut in half, and then we just look at either the left half or the right half. So since the problem's being cut in half over and over again, that just is stereotypical of using log, versus if you have, let's say, a problem where at each step n doubles. Now we're in exponential, right? So this is sort of the opposite when we're repeatedly cutting in half. That just means it's logarithmic. Okay, so really this is a solution. Big O time complexity for binary search is O of log n. And just final note, it doesn't matter in big O if you do, log, natural log. Sometimes we do LG, meaning log base 2. These are all different by just a constant, so they don't really matter. But that's the solution. That's Master Theorem with an example. Goodbye.